Welcome back to the deep dive. We have a really massive stack of research on the desk today, and honestly, reading through it felt a bit like we were straddling this weird line between advanced medical science and a classic sci-fi horror movie.
Oh, it really does. It is one of those topics where the sort of ick factor and the wow factor are just constantly fighting for dominance.
Yeah, exactly. So today we are talking about the doctor you swallow. And no, I don't mean like a very small physician, like in a cartoon or something. We are looking at a really comprehensive report from IEEE Spectrum from March 2026 regarding the absolute explosion of ingestible electronics.
Right.
We're talking about robotic pills that don't just dissolve, they hunt. They hunt for disease, they take biopsies, and they even perform surgery from the inside out.
It sounds completely futuristic, but the core message for you listening today is that the future is already wet and squishy and moving through your small intestine right now. We are witnessing a fundamental shift in medicine, moving from the era of passive pills to active agents.
Before we get into the mechanics of that, and we really do need to talk about mousetraps and dissolving needles because the engineering is just wild. Let's set the stage properly. I want you to picture the year 1966.
Ah, yes, the classic film.
The film is Fantastic Voyage. You've got a submarine, you've got a crew, including the legendary Raquel Welch, and they are shrunk down to microscopic size and injected into a scientist's body to save his life. It is the ultimate premise, right? A tiny team of doctors physically traveling through your veins to fix a blood clot.
It's an absolute classic. And for a long time, it was just that, pure science fiction. The idea that we could put intelligent agents inside the human body to perform surgery or deliver medicine seemed physically impossible. But here we are, it is March 2026, and while we haven't figured out how to shrink Raquel Welch or a submarine, we have figured out something arguably more important.
We don't need to shrink the doctors anymore. We're just building tiny robotic doctors instead.
Precisely. And that distinction is vital. We aren't sending humans in. We are sending autonomous systems.
So why are we doing this? I mean, standard medicine seems to work okay for a lot of things.
Oh.
Why do we need to send robots into our guts? Is the current system really that broken?
Broken might be a strong word, but incomplete and frustrating are definitely accurate terms. Think about the gastrointestinal tract, the GI tract. It is essentially a 30-foot-long tube running right through the center of your body. We have great tools for the entrance and the exit.
You mean endoscopes and colonoscopes?
Right. An endoscopy lets us see the stomach and the very top of the small intestine. A colonoscopy gives us a really great view of the large intestine, but in between, we have the small intestine. It is about 20 feet of narrow twisting, turning tubing. It is incredibly difficult to navigate with a traditional scope.
It's basically the dark continent of the human body.
Essentially, yeah. Reaching deep into the small intestine with a tube is incredibly difficult. It's risky, and it requires heavy sedation. And unfortunately, it's where a whole lot of disease hides. We're talking about inflammatory bowel disease or IBD Crohn's disease, celiac, small intestinal bacterial overgrowth, and specifically small bowel cancers.
And if you have an issue there right now,
Yeah.
what is the protocol? Because you can't just look at it easily.
It's a maze, a really frustrating maze. You start with blood tests, which are vague. They might tell you, hey, there is inflammation somewhere in the body, but not where.
Right. It just says something is wrong.
Exactly. You might do a CT scan, but that doesn't show you the surface texture of the gut lining, so you might completely miss early stage issues. So you're left with this massive blind spot in the middle of the patient.
And the treatment options aren't much better, are they? If I have inflammation in a specific, say, 5-centimeter patch of my small intestine, I can't just put a cream on it.
No, you take a systemic drug. You swallow a pill or get an injection that floods your entire body with medication just to treat that one tiny isolated spot. It's the definition of using a sledgehammer to crack a nut.
Because it goes everywhere.
Everywhere. You get side effects everywhere. Immune suppression, liver toxicity, all because the drug is interacting with perfectly healthy tissue purely because we can't target the delivery.
So the mission of the deep dive today, the mission of the engineers we are looking at, specifically the team at the MEM Sensors and Actuators Laboratory, or MSAL, at the University of Maryland, is to fix both the blindness and the sledgehammer problem.
That is the goal. They are trying to pack a diagnostic lab, a pharmacy, and a surgeon into a capsule the size of a large vitamin.
Let's rewind a bit to the history of this.
Yeah.
Because swallowing tech isn't brand new. I remember seeing headlines about camera pills years ago, like maybe the early 2000s.
You were thinking of the pill cam. That really hit the scene around then. And to be perfectly fair, it was a massive breakthrough. You swallow a capsule with a light and a camera, and it records a movie as it travels through you.
It's like a GoPro for your gut.
Pretty much a gut GoPro. But here's the critical distinction. The pool cam is a tourist. It's totally passive.
A tourist. I like that.
It floats along, it takes pictures, and it leaves. If it sees a tumor, it cannot stop. It can't poke it to see if it's soft or hard. It can't take a sample. It just records the footage and hopes the doctor spots the issue when they watch the video later.
So we are moving from passive observation to what exactly?
Active intervention. Autonomous intervention. The devices we are discussing today, these smart pills, are designed to sense the environment in real-time, process that data on board, make a decision, and then physically interact with the tissue.
That word autonomous is doing a lot of heavy lifting there. You're saying the pill actually decides when to act.
In some designs, yes, absolutely. Or it communicates with an external transmitter to get the green light from a doctor. But the capability for the pill to recognize, hey, I am at the disease site, is the real game changer. It transforms the device from a simple camera into an active robot.
Okay, let's walk through this journey. I am a patient. I swallow this robot. It drops into my stomach. What is it actually facing down there?
I feel like we take our digestion for granted. But from an electronics engineering perspective, the gut must be an absolute nightmare.
It is a totally hostile environment, an absolute jungle. First, you have the stomach, hydrochloric acid with a pH of 1 or 2 that will corrode standard electronics and dissolve many industrial glues instantly.
So the robot has to survive an acid bath immediately, right out of the gate.
Right. Then it moves into the small intestine. The pH rises. It becomes more alkaline. But now you have digestive enzymes. Proteases, lipases, things that are biologically designed to break down proteins and fats. If your sensor has a biological coating, the gut is actively trying to eat it.
And it's dark, it's wet, and there's no oxygen.
And it is constantly moving. Peristalsis is the muscle contraction that squeezes food along. So your robot is being squeezed, tumbled, and pushed through a tight tube filled with highly corrosive sludge. Lovely image. So how do they sense anything in that kind of chaos? You mentioned they are moving beyond just a camera. What are they actually looking for?
They're looking for chemistry. Visuals are great for big things like polyps or bleeding, but disease often starts at the molecular level long before you can see a bump or a lesion on a camera. So MSAL and other collaborative labs are building sensors to sniff out gases.
Farts, essentially.
Internal farts, yes. Things like hydrogen sulfide. It is a byproduct of bacterial fermentation. High levels can indicate localized bacterial overgrowth or serious issues with the microbiome composition.
Okay, so it is a gas detector. What else are they looking for?
Neurotransmitters, specifically serotonin and dopamine.
Wait, I thought serotonin was a brain chemical. That is the happiness chemical.
It's a common misconception. The vast majority of your body's serotonin, some like 90 to 95%, is actually produced in the gut.
No way. 90%.
Yep. It regulates movement and signaling in the intestines. There's a huge link between gut health and mental health, the gut-brain axis. Being able to map serotonin levels along the intestinal tract could totally revolutionize how we understand that connection.
That is wild. So the pill is essentially tasting the chemical soup as it floats by. But the report mentioned a specific sensor for pancreatic enzymes that really caught my eye because of how it solved that stomach acid problem you mentioned.
Ah, yes. This is a classic MSAL design innovation. They wanted to detect trypsin, which is a pancreatic enzyme in the duodenum. That's the very first section of the small intestine just past the stomach. But they had a major problem.
The stomach acid destroys the sensor on the way down.
Exactly. If you expose the delicate sensor in the stomach, the acid completely destroys it or fouls it up before you even get to the pancreas. So they needed a way to keep the sensor hidden until the exact right moment.
So what do? A timed release. Like, wait 30 minutes and then open the door.
No, because digestion speed varies wildly from person to person. 30 minutes might be perfect for you, but for me, the pool might still be sitting in the acidic stomach. They needed an environmentally triggered release.
How do they manage that?
They 3D printed a shell for the capsule and coated the sensor opening with a special pH-sensitive polymer. Think of it like a really smart candy shell. In the acidic stomach, the shell is hard as a rock. It protects the sensor perfectly.
But the moment it hits the small intestine,
the pH shifts from acidic to neutral or alkaline. The polymer detects that chemical shift and dissolves rapidly. That exposes the sensor right as it enters the duodenum.
that is so elegant. It just uses the body's own chemistry to flip the switch.
It effectively eliminates the need for complex timing circuitry or battery-draining active doors. It is passive intelligence.
Now, there was another sensing technology mentioned in the source material that sounded a bit more invasive, bioimpedance. This sounded like the pill is actually touching the wall of the gut.
Yes, this is the electronic touch. It is designed to detect something called leaky gut.
I have heard that term, usually in ads for expensive internet supplements. Is it an actual real medical condition?
The medical term is increased intestinal permeability. Your gut lining is supposed to be a tight barrier. The cells are stitched together by proteins called tight junctions that prevent bacteria and toxins from leaking out of the gut and into your bloodstream.
Okay.
In diseases like IBD or celiac, those junctions break down. The wall becomes porous.
But you can't see that with a camera, can you? A microscopic hole or a loose junction doesn't show up on a video feed.
Correct. But you can measure it with electricity.
How does that work?
Impedance spectroscopy. The capsule has electrodes on the outside coated in a conductive polymer. As it tumbles through the gut, it presses against the wall. It sends a tiny, tiny electrical current through the tissue.
Like a zap.
We are talking microamps. You wouldn't feel it at all. But the physics is really cool. If the tissue is healthy and the cells are tight, the electricity meets a specific amount of resistance. It flows in a certain predictable way.
And if it's leaky,
If the tissue is inflamed and leaky, the fluid balance is different, the cellular structure is compromised, and the electrical resistance drops or changes pattern.
so it is literally feeling the electrical resistance of the lining.
Precisely. It is tactile sensing. In tests with pigs, they actually induced leaky gut using a chemical called a calcium chelator, and the pill picked up the change in tissue impedance almost immediately.
That is fascinating. It's diagnostics without a biopsy. Just touch and go.
Well, without a biopsy is the goal for screening, but sometimes you really do need a biopsy. And that brings us to the most mechanical part of this deep dive,
The surgeon in the pill.
the biopsy bot.
This is the part that really blows my mind. We're talking about a pill that cuts a piece of you off and keeps it? How is that even safe? And more importantly, how do you fit a scalpel and a motor strong enough to cut flesh into a vitamin?
The power problem is the biggest hurdle here by far. Cutting tissue requires significant mechanical force. The small intestine is slippery, it's elastic, and it's remarkably tough. To cut it, you need a sharp burst of energy. But a tiny coin cell battery inside a pill just doesn't have the horsepower to drive a heavy cutting motor.
So how do they do it?
They cheat. Or rather, they use physics to their advantage. They separate the accumulation of energy from the release of energy.
Talk me through that.
Think of a mousetrap.
Okay.
When you set a mousetrap, you are putting a lot of energy into the spring. You do that before you put it on the floor. You use your big human muscles to wind it up. The trap sits there holding all that potential energy waiting.
And when the mouse touches the cheese, snap. Instant release.
Exactly. The MSAL team uses a miniature portion spring inside the capsule. Before the patient swallows it, the engineers wind that spring up tight. It is packed with potential energy.
But what holds it back? You can't use a normal latch right, because unlatching a physical lock would require a motor.
This is the genius part. They use glue,
Glue.
a special thermal adhesive. They actually glue the latch open, and embedded right in that glue is a tiny microscopic heater.
I think I see where this is going.
When the pill reaches the target area, the battery sends a weak trickle of electricity to the heater. It doesn't need much power at all, just enough to warm up the glue. The glue melts or softens.
And the spring takes over.
S&FE. The spring releases all that stored energy in a fraction of a second. That massive force drives a cutting tool, usually a rotating bladed scraper or a cylindrical biopsy punch, straight into the tissue.
That perfectly solves the force problem. You do the heavy lifting before you swallow the pill, the battery just pulls the trigger.
Exactly. It is called a low-power release mechanism, and they use direct laser writing to sharpen these tiny blades at a microscale so they cut cleanly.
But hold on, you've just cut a piece of my intestine. Now I have a loose chunk of flesh floating around in my gut. That seems pretty unhelpful.
It would be totally useless. You need to retrieve it. The mechanism is designed so that the cutting action itself creates a scooping motion. As the blade rotates, it drags the tissue sample inside the capsule body.
And then what?
And then the rotation finishes by closing a hatch. It seals the sample inside a sterile chamber. This is absolutely crucial because the pill still has to travel through the large intestine, which is full of bacteria. You don't want to contaminate your clean sample from the small bowel with the absolute mess in the colon.
So it grabs the sample, slams the door, and locks it down.
Correct. It is safely secured for the rest of the journey.
And then I have to fish it out of the toilet.
There's no getting around that part yet, sadly. It is the very low-tech bookend to a highly high-tech story, but if the alternative is surgery or a complex endoscopic procedure under heavy sedation, most patients would probably gladly take the fishing expedition.
Fair point. I would definitely rather sift than be sedated.
Yeah.
So we have the sensor and we have the surgeon. But let's talk about the pharmacy, because diagnosing is really only half the battle. If the robot finds inflammation, can it treat it?
This is the theranostic concept, therapy plus diagnostics, and this directly addresses that sledgehammer problem we talked about earlier.
Right, flooding the whole body with drugs to treat one spot.
If we can get a pill to deliver medication only to the disease spot, we can use much, much higher concentrations of the drug because we don't have to worry about it affecting the liver or the kidneys or the immune system globally.
But how does a pill inject a wall? It doesn't have arms.
Actually, it kind of does. They use cantilevers.
Cantilevers, like on a suspension bridge.
In MEMS terminology, think of them like tiny diving boards tucked into the side of the capsule. When the pill gets a signal, actuators push these arms out. They extend from the body of the pill and press hard against the intestinal wall.
And on the end of the arms.
Microneedles.
Of course. Why am I even surprised at this point?
These aren't the needles you see at the doctor's office. They are barely visible to the naked eye. The arms press these microneedles right into the lining.
Does that hurt? I mean, needles in your gut sounds painful.
Interestingly, no. The intestine actually has very few pain receptors for sharp trauma. It senses stretching and bloating like gas pain, but it doesn't really feel a pinprick the way your skin does, so it should be totally painless.
Okay, so the arm extends the needle, pokes the tissue. Then what?
There are a few flavors of this, and the variety is really fascinating. One is the hollow microneedle. It acts exactly like a tiny syringe. A reservoir in the pill pumps liquid drug through the needle directly into the tissue.
A direct, targeted injection.
Yes, but there's a cooler version involving dissolvable needles.
The needle is the drug.
Exactly. You mold the drug itself into a sharp, rigid spike using a binding polymer. The arm pushes the spike into the wall and then breaks it off.
It just leaves the needle behind.
The needle stays embedded in the tissue, acting as an anchor, and the robot retracts its arm and floats away. The needle then slowly dissolves over days, releasing the drug right where it is needed most.
That is brilliant, because the pill can't stay there forever, right? It's moving with the food. This way it plants a flag and keeps moving.
It parks the bus just long enough to drop the payload. And they are even experimenting with soft needles for more delicate tissues.
How do you puncture something with a soft needle?
It's more of a sponge mechanism. The arm pushes the soft porous needle against the wall. The pressure physically compresses the sponge, squishing it, and jets the drug out onto the surface of the tissue. It is for topical application rather than deep injection.
It sounds like 3D printing is sort of the unsung hero of all this.
Oh, absolutely. None of this would be possible without microscale 3D printing. They can tailor the shape, the sharpness, and the dissolution rate of these needles with incredible precision. They can literally print a needle that is sharp enough to pierce but dissolves at a highly specific controlled rate.
Okay, I want to circle back to something you mentioned briefly. Power. You said the mousetrap solves the force problem, but you still need electricity to run the sensors, the microheater, for the glue, the wireless transmitter to talk to my phone.
And that is the Achilles heel of this entire industry. Batteries are just incredibly bulky.
How much space do they actually take up in there?
In a typical smart capsule, the silver oxide batteries, which are basically coin cell wash batteries, take up 30 to 50% of the total internal volume.
That's huge. Imagine if half of your car's interior was just the gas tank.
It severely limits what you can pack in there. You want a bigger drug reservoir. You can't, the battery is in the way. You want a better camera or more sensors, no power for it. So there is a massive push for weird science solutions to power these things.
Give me the weirdest one. I am ready.
How about a battery that runs entirely on your stomach acid?
I feel like that actually makes too much sense. We have a literal tank of acid down there.
Researchers at MIT built a voltaic cell. They put zinc and copper electrodes on the outside of the capsule. When it hits the stomach acid, the acid acts as the electrolyte, the conducting fluid between the metals.
So you, the patient, become the battery acid.
That is metal, literally.
But that only works in the stomach, right? Once you hit the small intestine, the acid is neutralized.
Correct. It is a short-term power boost for tasks in the stomach.
Yeah.
So another team at SUNY Binghamton is working on microbial fuel cells.
Bacteria power.
Yes. They package spore-forming probiotic bacteria inside the pill. These bacteria remain dormant on the shelf, but when you swallow the pill, The moisture in your gut wakes them up. They start eating the nutrients around them, the glucose in your gut, and their metabolic process naturally generates electrons.
So the bacteria eat my lunch, and in return, they power my robot.
It is the ultimate symbiosis, a living biological battery.
That is incredible. But what about the motion? You said the gut is always moving and squeezing. Can we use that mechanical energy?
That's the third avenue they are exploring, piezoelectric harvesting. MSAL is heavily researching this. As the gut squeezes the pill through peristalsis, that mechanical pressure bends a specific piezoelectric material inside the capsule.
And bending it creates voltage.
Right. It turns the gut's violence into electricity. If they can crack that, the capsule could theoretically run forever, or at least as long as it's inside you, without needing a chemical battery at all.
Infinite range. That would be the real breakthrough for these devices.
It would fundamentally change the design constraints. But until then, we are stuck with batteries. And that brings up the big safety question.
Yeah, let's go there. Because swallowing a battery is usually something we explicitly tell toddlers not to do.
For very good reason. If a battery leaks inside you, it causes severe chemical burns.
So how do we trust these things? How do we know it won't leak?
Rigorous encapsulation. The batteries are heavily sealed inside biocompatible medical-grade polymers. They are tested to withstand pressures and acidity levels far higher than anything the human body can actually produce.
What about getting stuck? That is my personal nightmare. The robot gets lodged in a tight turn.
Retention is the primary clinical risk, especially if a patient has a stricture, which is a narrowing of the intestine due to scar tissue or a tumor. If the capsule is too big, it simply jams.
And then you need surgery to get the surgeon robot out. The irony.
It happens. That is exactly why there is so much focus on the form factor, making it highly hydrodynamic, smooth, and as small as humanly possible, and why doctors will often do a dummy run with the dissolving capsule first, just to make sure the path is completely clear.
And the data. We are beaming information out of our bodies from the inside. Is that safe? Are we cooking our insides with Wi-Fi?
No, the transmission power is incredibly low, much lower than your standard cell phone. The body is mostly water, which absorbs some of the signal. So the engineering challenge is actually getting the signal out to the receiver on your belt, not worrying about the tissue absorbing too much dangerous energy.
Okay, so let's zoom out a bit. We have the tech, we have the safety protocols. Where is this all going? What is the so what for the person listening to this deep dive right now?
So what is the shift from the hospital to the home?
Explain that transition.
Right now, GI diagnostics is an event. You feel sick, you make an appointment, you wait 3 weeks, you go to a hospital, you get prepped, you get sedated. It is expensive, it is time-consuming, and frankly, it's scary.
And because of that, people just don't do it.
Exactly. The report mentions that 41% of eligible U.S. adults are behind on their colorectal cancer screenings. That is millions of people rolling the dice because they do not want a colonoscopy.
So the vision here is to change that entire paradigm.
The vision is a package in the mail. You have vague belly pain. Instead of ignoring it, your doctor mails you a smart pill. You wake up, swallow it with a glass of water, and go to work.
It travels through me sniffing for hydrogen sulfide, checking for leaky gut, maybe sensing a polyp.
And it beams that data seamlessly to your phone. By the time you dispose of the pill the next morning, your doctor has a comprehensive high-resolution map of your small intestine health. No sedation, no hospital stay.
That totally democratizes access. If it is that easy, people will actually do it.
And we catch cancers early, specifically small bowel adenocarcinoma. Right now, we usually catch that at stage 4 because it hides in that massive blind spot we talked about. If we can screen for it easily, we catch it at stage 1. That saves lives.
That is incredibly powerful.
And the ultimate vision. The closed loop.
The semi-autonomous robot.
Right now, we have pills that sense or pills that deliver drugs. The holy grail is the multimodal device. A single unit that travels down, senses a lesion, stops, takes a biopsy, analyzes it on board.
Wait, analyzes it right there, inside the body.
That is the dream. Real-time pathology. It decides this is high risk and immediately deploys the microneedles to inject a therapeutic agent. Sense, decide, act. All in one single pass.
That is truly the fantastic voyage. We are removing the human doctor from the loop almost entirely.
We are blurring the line between biology and technology. We are using machines to heal us from the inside autonomously.
It is a lot to process. We spent the last decade getting used to wearable tech. You know, watches that count steps, rings that track sleep.
External monitors, sure.
Right. But are we ready for ingestible tech? A future where your yearly physical involves downloading data from a device that just traveled through your entire digestive system.
It absolutely challenges our definition of privacy and our relationship with our own bodies. Who owns that internal data? The pill manufacturer, the insurance company.
Oh, wow. I hadn't even thought of the insurance angle. They're like, we won't cover you because the robot saw you ate a whole pizza yesterday.
Exactly. The data implications are huge. But if the trade-off is catching pancreatic cancer before it becomes untreatable, I think most people will say, pass the water.
Ask the water, indeed. It is a brave new world, and it is swallowing us whole. Or rather, we are swallowing it.
A very vital distinction.
Thank you for joining us on this deep dive into the doctor you swallow. It has been a truly fascinating look at the work of the MSAL lab and the future of medicine. I really hope you all found this as mind-blowing as we did.
Always a pleasure to explore the cutting edge.
Keep those minds open, and maybe next time you take a simple aspirin, imagine what it could be doing if it had a tiny computer and a mousetrap inside. We will see you next time. Thanks for listening.